Hello everyone, in this video we would finally implement the multicolored tree search algorithm. Plenty of work to do, lots of code to write, but after we get done with this, we'll already come up with a framework that will be allowing us to tune our engine and essentially to see how by changing the moves that it generates by manipulating the way how the playouts are made, we can affect the playing strengths of the engine directly. So without further ado, let's get started because really we have lots of work to do here. So I'm continuing from the previous part and I just do open the source file. I'm going to where the multicolored research starts, and here we kickstart with defining the UCT constant. So constant UCT constant is going to be equal to 1.41. So that's the conventional value that is usually used. This constant is crucial in balancing exploration versus exploitation in multicolored research in general. The next thing, I want to create a node type structure, and this is going to be multicolored research tree node. Okay, the basic building block of the multicolored research. So here we'll have the state, and this would be the pointer to the board. So essentially, this is like the board variable that we've been creating, but in the context of the multicolored research, this is known as state. Then parent is the pointer to the parent node, if available. Okay. Then we have children, and children would be the list of these nodes. Okay. And finally, visits type integer and score type float 64. So let's adjust the layout nicely. Right, let's make sure we still can compile and run. Go build. Okay. And now finally, the most exciting part, so the multicolored research function itself. So I define the function called multicolored research. It would be taking the root state called, this is the pointer to the board structure, the root state of the board, and also the iterations, or they also call them playouts, but not to confuse board playouts with this overall general multicolored playouts. We call them iterations. It would return the type of integer which would be the best move, right? And we can start with creating the root node. So this is the very first thing to consider. So root node is going to be the address of the node, okay? And this is the fancy way to define root node in Go. So we do state would be equal to the root state. So here we do initialize the root node board structure. Parent is going to be equal to nil because this is the root node. It doesn't have any parents. Also children, for now, it's not going to have any children. We would create children later, in the later phases. The visits is equal to 0 since we did not yet made any visits. And the score is equal to the floating point value of 0. Okay. So, yeah, again, just want to make 100% sure we still may compile and run. Root declare but not used, missing return. Okay. So we essentially want to return the best move, but for now let's return 0, and we should have only one. Root declare but not used, but this is fairly okay. So Now we start so-called selection phase. Okay, so selection phase means the following. So we loop over the amount of iterations available. So we do for I assign the value of 0, I is less than iterations, and I plus plus. Just print fmt print line, so that we know that we have an interaction, multicolored research iteration like this, and the iteration itself. Okay, then creating a node variable, and we assigning the root to it, which we've just created. So this is the root node of our entire search tree, multicolored research. So this is the root node of that tree. And then we do for the length of node dot children is greater than 0, we do a loop. So we do this loop as long as the length of children is greater than 0. We don't have any children yet, but after the next phase would have some children. So in case, assuming that we already have some children here, so we create the best score variable. This is going to be equal to math infinite, like this, minus math infinite. And we also want to insert math here. Okay. Okay. Then we create the node called best child, so pointer to the node. And then we loop over the children, so for index and child, and assign the value of range of node children. Here we might find two scenarios. So let's define the score. For now equals to 0 floating point type. So if we might either encounter those nodes that do have some visits already, or those that do not have any visits. So if child visits is equal to 0, which means this node has not been visited before. In this case, we do score equals to plus math infinity. Okay, and otherwise we do use the fancy UCT formula, which helps us to figure out essentially which node do we want to select based on how many times the node has been visited and how much score did the node gain. So the UCT formula looks the following. So we need to take child.score divided by, then we need to make it a floating point 64, child visits, okay, then plus the UCT constant, balancing the exploration and exploitation, multiplied by the square root, so math sqrt square root, math logarithm of, we do again the floating point 64, no visits, divided by, convert to floating 64, child visits. I'm sorry, just messed up with parentheses here, like this, and I don't need this one. Okay. So this would be our score in case if indeed our node does have some visits. So let's make sure that it's syntactically correct still. Best declared but not used. Yeah, but they are syntactically correct. Great. And if it happens that score is greater than the best score, so we found a better node, right? This case, we do best score equals to score and best child equals to child. All right. Okay, best child declared but not used, but yeah, we didn't use it yet. And finally, we can say that in this case, node equals to the best child. Now this should not give any errors because, yeah, has been used. Everything has been used. Great. Okay. Then we go to the expansion phase. So over in here, if node dot state dot is game over. So if the game is going on, we can still generate moves. So this game is not over means that we still can generate moves. In this case, we want to expand our tree. So this is known as the expansion phase. We'll be creating new nodes within the tree. So here I just say expansion phase. Okay, and here we had the selection phase. Okay, selection phase. Here we have the expansion phase. We can start with generating moves. So moves equals, we are taking the current node state, which is the board instance, dot generate candidate moves. Okay, so these would be the moves, that one of which would potentially be taken as the best move. So again, a room for the further improvement. Okay, then we need to loop over the moves. So for index and move, and assign the value of the range of moves. So we loop over the moves here. We now need to copy the child state, create a child state, which would be copy the board. So node dot state dot copy, and within this new node, we would play a move. So it might also happen that the move, since the move generator gives us like pseudo-legal moves, we need to check whether the move is legal or not. So if it's not legal, we just skip. So we do if not child state dot play. So if it doesn't play, it returns 0 essentially. In this case, we just continue. But what to play? We play the move, and also we use child state site as the site to generate move for. So if this fails, we simply continue to the next move, right? So this might be the case, yeah. Otherwise, we did manage to play the move. So we create a child and assign the value, and again, fancy way to define a new node here. So address of node, and we have state, and this is the child state, and node children. So now we are entering the simulation time. So let's create the sim state variable, and we just create node state copy. So we create a copy of a current node node's board position. Okay, and from that position, within that copy, on that copy, we'll be performing a random playout. Okay, so we do create another variable called sim_result, so result of the simulation, which would be either 1 if black wins or -1 if white wins, and just do sim state.playout. So here we have the simulation phase. Okay. Finally, last but not least, probably the most interesting, the heart of the multicolored research algorithm is the backpropagation phase. So, for node is not equal to nil. So, while the node is not equal to nil, while it exists essentially, we want to do the following. So, this is the backpropagation section. Phase. Sorry. Yeah. So for a corresponding node, we backpropagate the visits. So visits plus plus, and then we do node.score plus equals simulated result. So accumulating scores effectively here, and also no equals to node parent. So this helps us to walk through the entire tree. Okay, to backpropagate the values from leaf nodes to parent nodes and then back to the very root node. Let's make sure we can still compile and run. Okay. What have I done? What have I done? So wrong. Yeah, just messed up things. Let me just redefine the child here. Okay, and yeah, obviously we have parent. We just need to define the child properly. Yeah. Okay. Seems now we can compile and run. Great. Okay. Now it might happen that the length of root children is equal to 0. In this case, we need to return like no move or pass. So if length of root children is equal to 0, in this case we just return 0. So this is like our pass. Okay, pass move. But otherwise, we may define the best move. For now, let's make it empty. And best visits equals to, let's make it -1. Now, we loop over the children within the root. So for index and child within the range of root children. So if it happens that child visits are greater than the best visits, then we do assign best visits equals to child visits, and best move equals to child state last move. Okay. After this, it would be quite handy to print some statistics so that we knew how many times each node has been visited and what would be the win rate for those particular nodes. So for the candidate moves for the root node, I mean. So fmt and print. So here we have the best move, and we have the root state square. We want to convert to square the best move that we have. Okay. Then want to print printf, use printf here. So the visits and the number. So here would be the root visits, and if root visits are greater than 0, then we do the win rate equals to root score divided by root visits. So we want to print this, so fmt printf win rate and two digits after the floating point, and a new line, and the win rate. And quite a similar thing we want to do for children. So if the length of root children is greater than 0, fmt print line child nodes, okay, and for index and child within the range of root children, I want to print the move and visits. Move would be a string, visits would be a digit. For the move, we use child state square to convert the integer to the human readable coordinates, yeah. And the move itself is child state last move, and also child visits, okay. Then again, if child visits are greater than 0, we define the win rate. It's very similar stuff here. This time we have child score divided by child visits, and print the win rate. And also here, just to make sure we're not confusing GUI, I'm doing just a print line, so because it might not always be the case that visits are greater than 0. Okay, so we just make sure that we have a new line. Otherwise, the best move would not be returned to the GUI, and we would not see the engine playing the move within the GUI. And now we return the best move. Okay, hold my breath and try to compile and run. Okay, undefined best visits 378. Okay, seems like all good. Yeah, we need to run the multicolored research now. So for instance, I don't need this. I just do multicolored research and the board, and let's give it 10 iterations. Okay, iteration 0, 1. Yeah, this is slow because the playout super slow now, taking up to 1500 moves, which is not the good thing to do. So I think we can simplify that, and we can also make it like with the similar results essentially. And we can probably go for this just now. Anyway, yeah, maybe the next video. I just don't want to put too many things. Yeah, so all the all the iterations has been completed, and these are the moves. So D16 had 4 visits. Okay, D4 only 2 visits. The win rate and the best move is D16. Yeah, it's much better now. So one last thing to do is, so I don't want this, and within the GTP I just do multi-colored tree search and board, and that's the 10 iterations. Okay, show board genmove for black, and it should now generate a move. And after it completes, we're trying this in the GUI. Okay. Okay, D4. Okay, and show board. Yes, and indeed D4 with black has been played. Yeah, great. So let's test this with the GUI. So I want to adjust the path to the engine to the latest version that we've created here. So this is tutorial bot 10. Okay, and go. Okay, so let's play with white, and here we go. So start generate a move. It takes time. Yeah, hopefully it would make it faster. I mean, at least within the same amount of time. More playouts would be done, because 10 playouts is like literally nothing. But already, assuming that we have this opening moves like playing the corner, some attack defense moves and random moves, so which one would be conceded? So if we have a look at just the bare playout, generate playout move, if I play here on Q4, the next move he would do, it would be attaching to the stone, usually. But with the multicolored research, this is not obviously the case. This still might be the case, but it may also try to consider developing territories, which would prove that, in particular, it's actually searching. Okay, but again, too few playouts to know for sure, so it might be quite a random result still. Yeah, but anyway, so like it's not attaching to the stone. It sort of tries to develop territory, although it knows literally nothing about this, which is cool. Yeah, let's see now. We'll probably start attaching to the stone, I guess. It will probably start, or maybe play a random move, also possible. I guess it would now start attaching to the stone. Yeah. Yeah, by the time it's thinking, I need to say that in order, so it decides to extend own group, because that's the case. So we may want to try to make those moves, candidate moves, to not contain weird moves like this, for instance, because it's not very good. But anyway, we can clearly see that it's trying to search according to what it's told to. And so to measure the accuracy of search, to measure that the search is bug free, which we would still need to check that out. Yeah, by the way, this is quite a good move. So it tries to do something with the corner. I quite like this. So let's just play away to see, maybe it starts attaching from somewhere. So to make sure, say we have like 5 candidate moves, and we know that one of those is crucial to be done, like saving the group or like killing the group if that's the life and death kind of thing. So we would see how many visits that move would have. What would be the So Sov tries to attack, which is cool. Let's give it another try. So with the smaller board size, where we can do just more playouts, just to make sure that the playouts are working properly, that more playouts result in a more accurate play. Just want to make sure that the search is working nicely. And then we would be working on 2 kind of heuristics. This move looks a little bit strange, but anyway. So 2 kind of heuristics. So the playout heuristics, so that should be as simple and as fast as possible. And it's better to have more playouts with less quality than fewer playouts with a better quality. Well, that's essentially a trade-off. But yeah, we can try both. So from this, what I want to say that from now on, we have a basic framework that allows us lots of experimenting. So this is not a plain engine yet, and I would even say I believe that probably this Monte Carlo research power version of the engine doesn't necessarily mean this is going to be more powerful, like stronger than the generate playout move kind of function. It's not obviously the case, I believe. This will probably be like just weird, even worse. But that's not because it's bad. That's because it operates mostly on placeholders. So generate candidate moves, placeholders, generate playout moves. At the moment, still serve a placeholder, so this might be improved later on. And again, for measuring the accuracy of the Monte Carlo research itself to get proper statistics and to visually see how properly it performs, it would be much easier and faster to check this out on a smaller board size like 9x9 or even less, so that like when we have enough playouts, we need to make sure that we'll be playing perfect moves according to the heuristics that has been given to it. Okay, so the heuristics might not be that good, so it still might be like losing many games, but we need to make sure that the heuristics works out exactly the way it has been programmed to make sure it's bug free. So lots of testing, lots of experimenting in front, and there won't be significant code changes within the next few videos, I believe. So I believe that the next few videos would be in the format of like slight code update, and then more likely emphasizing the demonstration of what has particularly changed, because again, those changes would not be as big, as complicated as those need some explanations or something. So rather simple, self-explanatory, tiny little changes. So I would rather just emphasize those, show those, like I do in the beginning of the video when an update comes. Probably, if that would be something more significant, then we'll write this in a corresponding video. Okay, guys, this is it from my side. Congratulations on reaching this milestone of working Monte Carlo research, and hope for more experimenting in the future videos. This is it from my side again. I'll see you next videos. Until then, and cheers.